Welcome everyone. My name is Rutu Joshi and I'm the session chair of this session. This session is titled Innovative Applications. Geosynthetics continue to serve an integral role in geotechnical and civil engineering applications. Innovations in geosynthetics, be it in manufacturing processes, use of new materials, development of novel products, or creative approaches in using geosynthetics, are critical in advancing their use to solve challenging problems of our time. As aptly said by Sir Ove Arup, a pivotal engineer of the 20th century, quote, "Engineering problems are underdefined. There are many solutions, good, bad, and indifferent. The art is to arrive at a good solution. This is a creative activity involving imagination, intuition, and deliberate choice," end quote. And innovation in geosynthetics is certainly a creative activity. The Geosynthetics Conference invites you to attend several engaging presentations in this session on innovative applications of geosynthetics by esteemed professionals in our field. A couple of things to note before we start the presentations. You will have the opportunity to ask questions during this on-demand session by clicking the questions button at the bottom of the video window. Your questions will be sent to the presenter to answer as soon as they are able to. To claim PDH credits for this session and any other education session, you simply need to click on the Claim Credit button on the conference homepage. From there, you will fill out the survey for any sessions that you attend. Please note that you will need to include the verification code shown in this session to verify that you did attend this session and ensure that you received the proper credits. With that, please enjoy the presentations.
Okay, everybody. My name is Fei Wang. I'm from Tardon State University. Today, I'm going to give a presentation with the title of Numerical Modeling on the Use of Geotextiles to Reinforce Area HDB Pipes Subject to Localized Ground Subsidence. And I have another two co-authors, Dr. Zhou and then Dr. Du. So Dr. Zhou was my former colleague at Southeast University in China, and then Dr. Zhou was our students back to China. Okay, for this presentation, I will have three things. First, I'm gonna talk about the problem statement. What is the motivation for us to do this kind of research? And then second, I will talk about the numerical modeling, the numerical model we used, and then the soil properties, material properties, and then the dimension of the model, and then the numerical cases we used in our research, and the numerical results analysis. And then the last one will be the conclusions we get from our numerical results. I think the pipe failure is very often in cities, and you probably have seen a lot of these kind of cases. Basically, when you have a big sinkhole and then you have the pipes breaks due to the differential settlement, or not a sinkhole, if you have a differential settlement caused by any reason, and then the pipes buried in the ground will fail, and then you will break the pipe. Okay, so that's the pipe failure caused by localized subsidence. I have a photo here, shows the severe, of this kind of pipe failure caused by the sinkhole over here. You can see a car in here, and then I think hopefully the person in the car, he was safe. Okay, so geosynthetics have been widely used to protect the pipelines. Prevent the pipeline from failure. Due to the localized subsidence. And then previous studies, and then the researchers have done a lot of research about this topic. And then the first ones, Kawabata, and then they did research using 5 layers of a geogrids, try to reduce the overall load above the HDB pipe. And then basically, when you reinforce the soil, and then you will limit the settlement, which will, lower the load transfer to the pipe when you have different settlement. Okay, Tafresh And then Kalaja in year of 2008, they used the geotextiles to reduce the deflection of pipes. And then Mirihajidi proposed to use the geocells to protect PVC pipes. And then Corey, they conclude that the geograce above the pipe can reduce the pipe deflection by 11% if you apply the load at the ground surface. And then Joe, basically my student, the co-author of this paper, and then we did the kind of research, and then we put the geotextile underneath the pipe, and then in the physical modeling in the laboratory, we find out the geotextile can really minimize the effect of localized subsidence to the HDPE pipes. But the problem we have over here, most of the existing studies just use the physical modeling or the physical model test in the laboratory, try to figure out the performance of the pipe reinforced by the geosynthetics, or try to figure out what will be the performance of the geosynthetics when we have different settlement and then we'll transfer to the pipe. Because the physical modeling, we cannot model all the cases. So the numerical modeling will be a very powerful tool to investigate, all the cases by changing some of the key parameters. That's the reason, or that's the motivation we did this research. Okay, the two figures on this slide shows the dimension of the numerical model and the mesh of the numerical model. So here the unit is a millimeter. So you can see we have like a 3D model. Due to the symmetry of this model, basically we only model half of the model. And then you may ask me why we use this kind of size. Basically the weight or the box is 2,000 or millimeter or 2 meters, and then also the other side also 2 meter things. So we have half is 1 meter. We have the depth is 1.1 meter. We have the diameter is 15 centimeters. Why we are using this kind of dimension? Because we did kind of a physical modeling. We just try to use the numerical model and then to simulate the physical model tests we did in the laboratory. That's the reason we use this kind of dimension here. In this slides, you will see the summary of the parameters or the properties of the pipe, soils, and then geotextiles. And then for the pipe, we have a modulus, we have Poisson's ratio, we have density. Basically, that's the typical values for the HDPE pipe. For the surrounding soils, and then we just use the sand, basically in the lab test or in the physical modeling test, we just use the sand. That's why we have this kind of parameters or properties for the surrounding soils. And then for the geotextiles, think the model test, and then it's kind of a reduced scale. So we use a lower modulus of the geotextile, and then the Poisson's ratio and the density, that's our normal. They are normal based on the database provided the manufacturer. This slide shows the summary of the numerical cases we did. Actually, we did 5 cases. In other words, we created 5 numerical models, try to investigate the effects of the reinforced location and the reinforced layer number. Basically, the first one is the baseline case. You can see we just have the geotextile reinforced at the bottom of the pipe or the pipe invert. We have only 1 layer. And then the case 2 and the case 3, basically we move the single layer of the reinforcement from the pipe invert to 0.2 meters from the invert, basically lower that by 0.2 meters. And then the case 3, we're lower by 0.4 meters, but we still have the single layer of reinforcement. Case 4 and case 5, instead of we only have one reinforcement, one layer reinforcement, we have 2 layers for case 4, we have 3 layers for case 5, and then also shows the location of the reinforcement. We are trying to use the numerical modeling to figure out what is the effect of the reinforced location and the layer number on the performance of the pipe reinforced by geotextiles. So the next question is, how can we generate the differential settlement or the localized subsidence in the numerical model? The way we did, we just apply the displacement at the bottom of the numerical model. But the displacement is not a uniform displacement. We have the displacement pattern really follow the subsidence pattern we did in the lab. Basically, the bottom of the box can be separated at 8 pieces. For each piece, we have 250 millimeter. And then we only lower the middle 4 pieces. And then by this kind of pattern, say we lower the middle 2 or the 2 at the center first by a certain amount. Then we will lower the other 2 adjacent to the middle 2 place, try to match a settlement. Then we'll form this kind of like a curve, the differential settlement. Okay, we're trying to match what we did in the lab tests. Before we do the numerical modeling for this research, we have to verify the numerical modeling procedure we use in this study is effective. So we should compare the numerical results with the measured results in the lab. The left figure shows the comparison of the pipe vertical displacement both in the model test and in the numerical modeling. So you can see, the lines really, that's the numerical results, but the data points, those are the measured results from the model test in the lab. So we can see they match very well. That's the pipe vertical displacement. And then we also have a table over here shows the vertical pressure at the pipe top. And then we have 2 measuring sections, measuring section 1 and then measuring section 2. The measuring section 1 is exactly in the middle of the pipe. The measuring section 2 is 200 millimeters from the middle. And then, those 2 measuring sections really, we mirror the pressure, we mirror the displacement. And then you can see the vertical pressure at both measuring sections shows like the measured one in the lab and the numerical results, they kind of close. Even we have some errors, but we can still say, overall, the numerical modeling procedure we use in this study is effective to do the numerical research. This slide shows the effect of a reinforcement location on the pipe performance, or to be more specific, the vertical displacement of the pipe. So we have 3 figures over here, and then basically it shows like the different maximum displacement at the model bottom of the model. And then we have 10 millimeter, 30 millimeter, and 50 millimeter. And then for each figure, you have 3 curves, show 3 cases. So the top, and then the first curve, the top curve, that's when you reinforce the pipe at the pipe bottom. The middle one, that's the, when you reinforce a pipe like 0.2 meters from the pipe bottom. And then the bottom curve, that's 0.4 meters from the pipe bottom. So compared to the displacement of the model bottom, and you can see for all those 3 cases really has kind of a positive effect to reduce the vertical displacement of the pipe, but the reinforcement at the pipe bottom had the best performance. The other two cases had a little bit larger displacement. The reason for that is if you reinforce a pipe a little bit far from the pipe bottom, and then the layers between the pipe and the geosynthetics, the soil layers, will still have displacement or deformation. Those kind of deformation will transfer to the pipe to enlarge the vertical displacement of the pipe. This slide shows the vertical displacement of the geotextiles, basically when you have different maximum displacement at the model bottom. Okay, so that will be the same trend as what we had for the vertical displacement of the pipe. But you can see, when you reinforce the pipe at the pipe bottom, and then the vertical displacement of the geotextile also had the minimum vertical displacement, had the minimum value. Okay, so the reason for that, and then when the settlement propagates from the bottom to the pipe, and then when the settlement reach the geotextiles, and then the geotextile really can just spread the settlement to two sides, and then use the tensile force in the geotextile, and then to reduce the settlement. But if you reinforce the pipe a little bit far from the pipe, and then even we have the tensile force can spread the force, but when the displacement transfer to the pipe, and then same reason, the layers between the pipe and then the geotextile can still have displacement influence the performance of the pipe. This slide shows the effect of a geotextile layer number. Basically, we have a single layer, we have two layers, we have three layers, and then of the reinforcement. What will be the performance of the pipe, or what will be the vertical displacement of the pipe? And then, so three figures shows you have three different maximum displacement of the model bottom. Okay, you can see, and then those three cases, basically you have single layers, two layers, three layers, and then the vertical displacement, they are almost the same. In other words, the effect of the reinforcement layer number is insignificant. So in other words, try to reach the maximum cost-effective solution. We should only use single layer reinforcement. From the above, numerical results, and then we can have the following conclusions. The first one, geotextile placed or installed at the pipe bottom had the best performance. The second one, the maximum vertical displacement of the geotextile is larger than that of the pipe in the same case. Okay. The third one, the increase of the reinforcement layer number could not influence the results significantly. So overall, in conclusion, if we have a pipe influenced by the localized subsidency, we should reinforce the pipe at the pipe bottom, only use single layer. Thank you. Any questions? If you have any question, you can also shoot me an email at feywang@tarleton, tarleton.edu. Okay.
Welcome to the virtual IFAI Geosynthetics Conference 2021. This discussion is on the effectiveness of geosynthetic protection of buried pipes from static loads based on pipe stiffness. The effectiveness of geosynthetic protection of buried pipes for static loads based on pipe stiffness was written by authors Ryan Corey, Deep Khatri, and Professors Jihan and Robert Parsons at the University of Kansas Civil, Environmental, and Architectural Engineering School. The purpose of this research was to determine the practicality and level of benefit of including geosynthetics to protect pipes. Do geosynthetics protect pipes and buried conduits? Is there ways that they can be improved or optimized? And research concentrates on flexible pipes with near-surface loads. Here is a short list of previous work on the protection and strengthening of pipe backfill. This is the presentation outline. We will cover laboratory tests, a numerical calibration of the laboratory tests, a parametric study based on the numerical calibration, and finally, conclusions. Full-scale laboratory tests were performed at the University of Kansas. On the left is an isometric of the test apparatus, which was a 3 meter wide by 2 meter long by 2 meter tall geotechnical box. Above the box was a movable frame with an actuator and a 300 millimeter or 12-inch diameter loading plate. The maximum load determined to be used on this test was 689 kPa, or approximately 100 psi. Inside the box, a fat clay was used as in situ soil to act as a material outside the trench. The trench was created with forms while the clay was compacted on the outside of the forms. The resulting trench was 1.22 meters wide and 1.14 meters deep, or approximately 4 feet wide by 3'9" deep. After completion of the trench, a 152 millimeter 6-inch bedding was placed in the bottom of the trench. The clean aggregate bedding was a maximum 3/4 inch crushed stone aggregate. A 600 millimeter or 2 foot diameter pipe was placed and centered in the trench, and 7 1/2 layers of 152 millimeter lifts were placed on each side of the pipe simultaneously. A 2.5 by 2 meter long polypropylene geogrid was centered above the pipe. And finally, a 230 millimeter layer of compacted AB3 base course was placed above the pipe in 2 lifts. The flexible steel pipe was a 610 millimeter or 2 foot diameter pipe. Steel reinforced HDE pipe was selected for this test. The pipe wall has 13 millimeter high ribs spaced 25.4 millimeters on center. The outstanding rib runs around the circumference of the pipe. In the diagram on the left, you see that the x-axis runs parallel to the pipe, where the y-axis runs perpendicular pipe in the circumferential direction, to give you an idea of the orientation of the reinforcing. To further clarify, here is a photo of an example of a steel reinforced HDPE pipe being installed in a separate project. A parallel plate load test was also run on the pipe section as part of the project. The parallel plate load test measured a pipe stiffness of 327 kPa. For comparison, an elastic solution of the pipe stiffness, shown in a dotted line, equated to about 478 kPa. The geosynthetic used for the laboratory test was a punch-drawn biaxial polypropylene geogrid. Stiffness of the geogrid was 990 kilonewtons per meter in the machine direction and 660 kilonewtons per meter in the cross direction. The geogrid was placed above the pipe with the machine direction parallel to the pipe. Fat clay used as the in situ soil was determined to have a maximum dry unit weight of 15.4 kilonewtons per meter cubed. The clay was compacted at a density of 14.5 kilonewtons per meter cubed, near the optimum moisture content. The backfill was a clean aggregate with a maximum size of 3/4 inch or 19 millimeters with a mean particle size of 11.2 millimeters, or approximately 1/2 inch. The backfill was poured in at a density of 14.5 kilonewtons per meter cubed, or a relative density of 45%. The AB3 was a well-graded base course, which was compacted with a plate compactor to 95% of maximum dry density and a moisture content of approximately 10%. Instrumentation. 2 vertical displacement transducers were placed in the pipe to measure the relative distance from the crown of the pipe to the invert of the pipe. 1 vertical displacement transducer was placed directly under the loading plate, and the second vertical displacement transducer was placed 300 millimeters from the loading plate. A third displacement transducer was placed horizontally to measure the relative horizontal deformation of the pipe. A telltale was attached to the top of the pipe and a static datum to tell the overall displacement of the crown of the pipe. Lastly, the displacement of the loading plate was measured. A pressure cell was also added 51 millimeters or 2 inches above the crown of the pipe, directly under the loading plate. The 300 millimeter plate was used to load in pressure increments of 68.9 kPa, 10 psi, or 600 up to a maximum 689 kPa or 100 psi. After the maximum load of 689 kPa was reached, the load was reduced in the following steps: 413.4 kPa, 137.8 kPa, and 68.9 kPa back to zero pressure applied. 2 tests were run, once with reinforcing and once without reinforcing. Numerical analysis. A numerical analysis of the laboratory tests was run with a FLAC 3D finite difference model. An axis symmetric model was used. The fat clay was modeled as an elastic material with a bulk modulus of 20.8 megapascals and a shear modulus of 9.6 megapascals. The AB3 was modeled as an elastic, plastic, Moore-Coulomb failure type material, and the AB3 material stiffness was modified by the GeoGrid. The reinforcement base core stiffness was calibrated by the measured plate settlement at the surface. This resulted in a bulk modulus of 22.7 megapascals for the reinforced condition and a bulk modulus of 13.7 megapascals for the unreinforced condition. The clean crushed stone aggregate backfill was modeled with the gap yield constituted model, allowing the nonlinear strain softening to be duplicated. On the left are the parameters that were used for the constituted model, and on the right are the FLAC models of a triaxial test, showing that the actual triaxial test with the aggregate and the FLAC models 3 different confining pressures. Plate bending stiffness and axial stiffness of the pipe in the model were set to match the orthotropic stiffnesses of the pipe. The bending stiffness of in the circumferential direction, the y-axis, is approximately 44,500 times as stiff as the plastic shell in the x direction. Likewise, the axial stiffness in the y direction is approximately 100 times as stiff as in the x direction. This is due to the steel reinforced ribs running around the pipe in the circumferential direction. These are the results of the lab tests in solid lines and the FLAC numerical models in the dashed lines. The reinforced tests in the numerical model and the laboratory model have the X marker, while the unreinforced condition has the solid diamond. On the left is the vertical plate settlement measured by the actuator with a maximum displacement of approximately 18 millimeters. And on the right is the vertical pipe deflection, which was measured at 4 millimeters difference, that is from the crown of the pipe to the invert of the pipe, a 4 millimeter shortening of the pipe. And finally, for the results, the measured pressure near the crown of the pipe is shown on the left, with a maximum pipe pressure at the crown of 121 kPa for the unreinforced condition and 105 kPa for the reinforced condition. So we measured in the laboratory results a 10% approximate reduction in the displacement and a 10% reduction in the vertical pressure at the crown of the pipe. While the numerical model had mixed results, the general response of the numerical model matched the laboratory models, but the difference between the unreinforced and reinforced conditions was difficult to capture. How can we get more benefit from the inclusion of GeoGrid or a geosynthetic? The design method for flexible pipe introduced the concept of bending stiffness factor and hoop stiffness factor for categorizing and projecting the response of buried flexible pipes. Here, M sub S being the constrained modulus of the soil surrounding the pipe, and EI over R being the modulus of elasticity, the moment of inertia, and the radius of the pipe wall. The hoop stiffness factor being consisting of the constrained modulus and the axial stiffness and area of the pipe wall. The pipe stiffness of the steel reinforced high-density polyethylene pipe has a bending stiffness, here shown in highlighted in yellow, that it is close to HDPE pipe unreinforced, and both are significantly lower than corrugated steel pipe or reinforced concrete steel pipe. We calculated a hoop stiffness factor of 0.026 because the steel reinforcing is much higher than an unreinforced HDPE pipe, which would be in the lower range of 1 to 10. The 0.026 is shown here with the red X. The vertical arching factor is the ratio of the measured pressure at the crown of the pipe versus the calculated pressure based on the soil prism directly over the pipe. And the slip and no-slip condition is based on the interface between the pipe and the backfill. From our experiments, the vertical arching factor is closer to the no-slip condition. So we have a pipe with a low bending stiffness, but a relatively high hoop stiffness. This made us want to investigate what types of pipe would benefit from GeoGrid reinforcement. To do this, we ran the same model with 5 different pipe stiffnesses by increasing the stiffness by factors of 4, 16, and 256, and lowering the stiffness by 1/16. We also ran the model in 8 conditions by lowering the hoop stiffness so that we could get in a range from 1 to 0.1. In Flax, it was easy to modify the bending stiffness factors by adjusting the plate bending and axial stiffness of the pipe. So the dy plate bending stiffness and EY plate axial stiffness were modified accordingly for each numerical run. As can be expected, as the pipe stiffness increases, the benefit of the GeoGrid reinforcement diminishes. Now, remembering this is relative stiffness, so the pipe that we use, a pipe stiffness of approximately 300 kilopascal, has a factor of 1 in these diagrams. So as we get to near a factor of 10 or a pipe stiffness of 3000 kPa, the inclusion of GeoGrid layer does not help with the pipe deflection and or the vertical pressure benefit decreases rapidly. As the hoop stiffness factor increases, now remember this is inverse to the wall stiffness, as the hoop stiffness factor increases, the benefit of the GeoGrid increases. for both the pipe deflection and the maximum settlement at the surface. Now this matches McGrath's diagram of vertical arching factor with the hoop stiffness. So at about 1, the vertical arching goes down, and at 1, the benefit of the GeoGrid increases. Conclusions. Of course, the more flexible the pipe is in bending and hoop stiffness, the more benefit will be achieved by including a geosynthetic. A pipe should have a hoop stiffness factor greater than 1 to see benefit from geosynthetic, and a pipe should have a bending pipe stiffness of less than 300 kPa. Questions or comments? I would love to hear from anybody who would like to reach out to me. They can reach out to me at ryanc@rtetech.com. And finally, I'd like to thank KU School of Engineering, Dr. Hahn, Dr. Parsons, my associate, Deep Khatri, and my employer, RTE Technologies. Thank you very much.
My name is Ming Zhu. I am a Director of Engineering with Watershed Geosynthetics. My presentation today is landfill closure with engineered turf cover. First, I'd like to acknowledge co-authors of the paper, my colleagues Dr. Brian Shaw and Mr. Rutu Josh. This is the outline of what we will cover today. I will start with an introduction of the engineered turf cover and compare it with traditional soil cover. After that, I will focus on several technical aspects of the engineered turf cover, including UV longevity, wind uplift, sand infill mobility, and landfill gas management. In the end, I will talk briefly the beneficial reuse of landfill cover for solar power. What is an engineered turf cover? Basically, it is a 3-component landfill final cover system that includes from bottom to top a structured geomembrane, an engineered turf, and a specified infill. The structured geomembrane serves as a hydronic barrier to separate waste from the environment and cut off infiltration into waste. The engineered turf is made of synthetic grass blades tufted into a double-layer woven geotextile backing. It provides UV and wind protection of the underlying geomembrane. The specified infill is a layer of minimum half-inch thick sand buried in the synthetic grass blades. It provides additional ballast against wind uplift. It also provides UV protection of the engineered turf geotextile backing and improves trafficability due to its friction. The figure on the left is a typical cross-section of the engineered turf cover. The picture on the right is a 3D illustration of the system with photos of 3 components. Traditionally, landfills have been closed with soil covers. The engineered turf cover was developed to address long-standing challenges with traditional soil covers, a few of which are listed here. First, soil covers need soils. Some sites may not have enough soils available, or they have soils, but the soils may not be suitable and do not meet technical requirements. Second, soil erosion has been one of the biggest challenges for soil covers, as it depends on soil quality, vegetation, and the ever-changing weather conditions. Third, soil cover integrity. For example, surface cracking and cover slope failures, which happen quite often. And last, post-closure maintenance, including mowing, revegetation, erosion repairs, which can be a never-ending burden on landfill owners. Here are some examples of poor vegetation and soil erosion, desiccation and cracking, and veneer slope failure of soil cover. As you can see, all the challenges with soil covers are related to the soil layers. Here is the area photo of the Baldwin County landfill in Georgia. Installation was complete in 2017 and the site is about 23 acres. Recently, the US EPA selected the engineered turf cover to close the Mississippi Phosphates Corporation Superfund site located in Pascagoula, Mississippi. The total closure area is over 220 acres, and the construction of the engineered turf cover is currently ongoing. The aerial photo was taken on December the 10th, 2020, and shows that part of the site had already been closed with the engineered turf cover. As I mentioned previously, the challenges with soil covers are related to the soil layers. By removing soil layers, the engineered turf cover provides more predictable and consistent performance that is less affected by changing weather and site conditions. As shown in this slide with a side-by-side comparison between a traditional soil cover and the engineered turf cover, the soil layers above geomembrane in the traditional soil cover are replaced by the engineered turf and specified sand infill layers. A direct result of removing soil layers is improvement of runoff quality, because there is no soil for erosion except for the thin layer of sand infill that has minimal potential for movement. Therefore, soil erosion is no longer an issue and stormwater runoff from the landfill becomes virtually clean. The two photos on the left shows the landfill surface with soil erosion before closure and the same site after being closed with the engineered turf cover. The two photos on the top right compare the concrete perimeter channels at the Berkeley County landfill, one showing sediments washed from the soil cover area and the other showing the virtually clean channel in the engineered turf cover area at the same site. The photo on the bottom shows the water samples collected from the Tangipahoa landfill. The sample on the left was collected from the soil cover area with a turbidity of 371 NTUs. The sample on the right from the engineered turf cover area with a turbidity of only 11 NTUs, a drastic reduction in turbidity. I mentioned that cover slope failure was one of the challenges with traditional soil covers. Here's another example of veneer-type slope failure of a soil cover, where the soil layer slipped over the underlying geosynthetic layer. The failure could be caused by saturation of soil, clogging of drainage, and or insufficient shear strength of soil geosynthetic interface. However, the driving force is the weight of soil layers. Removing soil layers removes the driving force behind cover failure. Therefore, the veneer-type soil cover failure is no longer a concern for the engineered turf cover. The figure on the right shows the results of interface shear testing between the engineered turf and supergroup net, one of the structured geomembranes. The results shows a peak friction angle of 36 degrees. Using this friction angle, the slope stability factor of safety was estimated to be 2.2 for a 3-to-1 slope and 1.8 for 2.5-to-1 slope. The engineered turf cover makes it possible to close landfills with existing steep side slopes, as long as the overall waste mass is stable. Let's look at some technical aspects of the engineered turf cover. One of the most frequently asked questions is how long the engineered turf cover will last. As we know, geosynthetic materials are subject to UV degradation under sunlight. For the engineered turf cover, the geomembrane is covered by the engineered turf and infill and therefore protected from direct exposure to sunlight. Results of the extensive study by Geosynthetic Research Institute indicate that a covered geomembrane can last more than 400 years. For the engineered turf, the synthetic turf blades or fibers will be exposed to sunlight, so the longevity of the turf fibers will determine the longevity of the engineered turf cover system. Real-world testing was conducted on the engineered turf fibers at the Atlas Weathering Facility in New River, Arizona. As indicated by the UV radiation map, the facility is located in the area with the highest radiation in the US. Samples of fibers were placed on panels directly facing 45 degrees south, and the testing was conducted according to ASTM standards. The samples were connected from the test field after 1.3, 5, 7, and 10 years and sent to an independent geosynthetic lab for tensile strength testing. The tensile strength after exposure was compared to the original tensile strength to obtain the percentage of retained tensile strength. The data points were plotted in the figure here. Based on the 10-year data, the half-life of turf fiber, which corresponds to 50% retained tensile strength, was projected to be over 100 years, as shown in the figure. In addition to the test at the weathering facility, the turf fiber samples from real projects were collected and tested. The results of retained tensile strength from field samples were compared to the results from the weathering facility. The two blue squares are for samples connected from the softly filled landfill after approximately 5 years of installation, and the two red circles are from the nacelle ground landfill after approximately 7 and 8 years of installation. As you can see, the 4 data points are either at or above the line that represents the data from the Atlas weathering facility, which provides confidence of the data used to project the half-life. As more engineered turf cover projects get older, we will be collecting more samples from the field to further verify the projection. A wind tunnel test was conducted at Georgia Tech Research Institute in July 2010. The engineered turf cover was installed on a flat surface and tested at a wind speed of up to 120 miles per hour. The photos on the left are snapshots of the test at different wind speeds. The measured pressures on the engineered turf were plotted as a function of wind speed in the figure. Positive pressure is uplifting. No uplift of the engineered turf cover was observed during testing. The measured maximum uplifting pressure, which was about 0.12 psf, was actually less than the self-weight of the engineered turf. As wind speed increased, the force on the engineered turf cover changed to downward force as the turf blades bent towards the ground by wind. Additional wind tunnel tests were conducted at the Iowa State University in 2018 and 2019. The tests were conducted on scaled landfill models with 2 side slopes and a top deck. One of the test models is shown in the photo on the left. Wind pressure coefficients, C sub P, were obtained from the wind tunnel tests and plotted in the figure on the right. The coefficient is an indicator of wind pressure. A positive coefficient corresponds to downward compression, and a negative value corresponds to upward lifting or suction. The figure shows the test results for both the engineered turf cover, labeled as closure turf, and an exposed geomembrane without turf. Two things to point out. First, the test results of the exposed geomembrane show clearly two peaks of suction near the two crusts, which is consistent with field observations for exposed geomembrane. Second, the peak coefficient value for the engineered turf is significantly lower than for the exposed geomembrane, which shows the effectiveness of the engineered turf to protect the underlying geomembrane from wind uplift. The wind pressure coefficient can be used to calculate the magnitude of wind pressure on the engineered turf cover surface. Large-scale rainfall simulation test was conducted at the TRI facility in South Carolina to evaluate hydraulic performance of sand infill under rainfall events. Here's a photo of the test setup. The engineered turf cover was tested under simulated rainfall intensities at about 2 inches and 4 inches per hour with nearly zero sand loss, and at 6 inches per hour with only 0.12% cumulative sand loss, which is equivalent to about 0.1 tons per acre. As a comparison, the maximum annual soil loss for a soil cover is 2 tons per acre. The engineered turf cover clearly outperforms traditional soil cover systems regarding soil erosion. Large-scale channel erosion test was also conducted at the same TRI facility. The test was conducted in a rectangular flume with sequential tests and increasing flows. The flow depth, velocity, and sand thickness change were measured during testing. Tests were performed for different sand materials, and the technical specifications of sand infill were developed based on the hydraulic test results. The photos at the bottom show the hydraulic flume and water flowing over the engineered turf cover during testing. The specified infill has a minimum thickness of 0.5 inches. It is a coarse and angular sand that provides hydraulic shear resistance to minimize potential sand movement in the field. It must meet technical specifications of angularity, grain size distribution, and specific gravity. It is typically supplied from local sources according to the technical specifications. The photos on the left show examples of sand infills. The figure on the right shows the technical requirements for the sand infill. The two dashed curves are the upper and lower bounds for the grain size distribution of the sand infill. The technical specifications were developed based on the hydraulic tests that I just described. Landfill Gas Connection and Control System (GCCS) is a critical component of landfills, especially MSW landfills. The engineered turf cover can be integrated with the conventional landfill GCCS. The photo on the left shows the engineered turf cover and vertical gas extraction wells. Pressure relief valves have been developed for the engineered turf cover to protect it from potential gas uplift during a shutdown of the landfill gas flare system or due to a malfunction of the landfill gas connection system. The figure on the right shows a pressure relief valve installed in the field with the engineered turf cover. After a landfill is closed, it leaves with a large unused space that can be reused for solar power generation. The engineered turf cover makes an ideal foundation for solar development because there is no overgrown vegetation or soil erosion, and therefore it requires minimal maintenance. This photo shows the power cap system installed on the engineered turf cover at the Chadwick Road landfill, Georgia, as part of a demonstration project. The PowerCap system has been custom designed for direct installation on the engineered turf cover. It does not require the racking system for the traditional solar system. It can be installed on both top deck and side slope to increase the power generation capacity of the landfill. This is the end of my presentation. Thank you for your time and attention.